Welcome to this short video. We start by setting up the central idea behind machine learning by contrasting two ways of thinking. Traditional programming starts with rules and data to produce answers, while machine learning works in the opposite direction, using data and answers to infer the rules. That shift is what lets models discover patterns at scale and make predictions on new, unseen examples. To understand how machine learning works under the hood, we must look at its core logic, which represents a shift from deductive logic to inductive reasoning. Traditional programming is rooted in deductive logic. You supply explicit rules and data, and the computer computes the answers according to the formula $text rules plus text data equals text answers $. Machine learning flips this entire paradigm on its head by utilizing inductive reasoning, operating on the formula $text answers plus text data equals text rules $. By feeding the system known answers alongside data, ML automates the discovery of underlying correlations within massive datasets, mathematically deriving patterns to accurately predict unseen data. Here, the focus moves to linear algebra, which gives data a mathematical structure the model can work with efficiently. Scalars, vectors, matrices, and tensors are just different ways of organizing information, and that organization is what makes vectorized computation possible. The key takeaway is that raw data becomes a format that GPUs and learning algorithms can process quickly and consistently. Before any learning can take place, raw data must be translated into structured mathematical formats through linear algebra. Data is converted into mathematical constructs known as tensors. This enables vectorization, allowing algorithms to process thousands of data points simultaneously on high-performance GPUs. While linear algebra structures the data, calculus serves as the primary engine driving learning and optimization. As the mathematics of continuous change, calculus answers a fundamental question. If I tweak the model's internal weights slightly, how much will the error change? By using derivatives to measure the slope of a function, the algorithm learns precisely which direction to adjust its internal parameters to reach minimum error. Furthermore, the chain rule provides the complete mathematical foundation for backpropagation, allowing error signals to flow back through neural networks to tune the system. Machine learning rarely deals in absolute truths. Instead, it operates in probabilities, aiming to maximize the likelihood that predictions align with reality. Statistics provides the framework to understand the data landscape, evaluating concepts like mean, variance, and the bias-variance trade-off to ensure the model discovers generalizable patterns rather than just memorizing noise. Probability then builds on this by leveraging Bayes' theorem to dynamically update beliefs as new evidence comes in. For example, given an email statistical distribution, a model can evaluate the evidence and determine there is a 98% probability it is spam. This slide introduces the loss function, which is how a model measures whether it is getting closer to the right answer. In regression, mean-squared error penalizes the distance between predicted and true values, while classification uses cross-entropy to judge how well probabilities match the correct category. In both cases, lower loss means the model is doing a better job. To improve over time, a system needs a precise way to measure its own mistakes, which brings us to the loss function. The loss function mathematically quantifies right and wrong. A high loss indicates poor model performance, while a zero loss represents perfection. Gradient descent is the search process that pushes the model toward better performance. All of these mathematical principles converge in gradient descent and the continuous loop of the machine learning lifecycle. Gradient descent acts as a mathematical search for perfection, navigating a lost landscape where setting an optimal learning rate is critical too small and the model converges too slowly, too large, and it risks overshooting the minimum error. The contour map shows how the path can be smooth and efficient with a small learning rate, or unstable when the learning rate is too large. The main idea is simple. Keep moving downhill on the error surface until the model finds a good solution. This final slide ties everything together into one training loop. Data moves through a forward pass, produces a prediction, gets evaluated with a loss, then uses calculus and gradient descent to send updates back through the model. The cycle repeats many times, and that repeated refinement is what turns the earlier math into a practical learning system.